Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 47, in which I will discuss some theorems on order of an integer, modulo m, and primitive roots. Now we prove a theorem. Theorem is if orders of a and b modulo m are small r and s respectively, with GCD of r and s equal to 1, then order of a multiplied by b modulo m is r multiply s, or order of a modulo m equal to r, order of b modulo m equal to s, and GCD of r and s equal to 1 implies that order of a multiplied by b modulo m equal to r multiply s. Now we prove this. Prove. Given that order of a modulo m equal to r, therefore GCD of a and m equal to 1 and a to the power r is congruent to 1 modulo m, r be the least positive integer. Let this is number 1. Again, given that order of b modulo m equal to s, therefore GCD of b and m equal to 1 and b to the power s is congruent to 1 modulo m. S be the least positive integer. Let this is number 2. From 1 and 2, GCD of am equal to 1 and GCD of b and m equal to 1 implies that GCD of a, b and m equal to 1. This is number 3. Let order of a, b modulo m equal to t implies that ab to the power t is congruent to 1 modulo m, t be the least positive integer. Let this is number 4. Raising power r in 4, we get ab to the power rt is congruent to 1 to the power r modulo m, implies that a to the power rt multiply b to the power rt is congruent to 1 modulo m. Let this is number 5. Raising power t in 1, we get a to the power rt is congruent to 1 to the power t modulo m. Implies that a to the power rt is congruent to 1 modulo m. Multiplying both sides by b to the power rt, a to the power rt multiply b to the power rt is congruent to b to the power rt modulo m. Let this is number 6. Therefore, from 5 and 6 we get, here in left side we see that a to the power rt multiply b to the power rt, here also be the same. Therefore, comparing right side we get b to the power rt is congruent to 1 modulo m. This is number 7. Comparing 2 and 7, we get here b to the power rt is congruent to 1 modulo m in 7. In 2, b to the power s is congruent to 1 modulo m and s be the least positive integer. Therefore, s divides rt. Let this is number 8. Since given that GCD of R and S equal to 1, therefore from 8, here GCD of R and S is 1, that is R and S are relatively prime to each other, hence S divides T. This is number 9. Raising power S in 4, we get, here we raise the power S, we get AB to the power TS is congruent to 1 to the power S modulo M. Implies that A to the power Ts multiply B to the power Ts is congruent to 1 modulo M. Let this is number 10. Raising power T in 2, we get B to the power St is congruent to 1 to the power T modulo M. Implies that B to the power St is congruent to 1 modulo M. Multiplying both sides by A to the power St, a to the power st modulo m. Let this is number 11. From 10 and 11, we get here in left side we get same thing. Therefore, a to the power st is congruent to 1 modulo m. A to the power st is congruent to 1 modulo m. This is number 12. From 1 and 12, we get in 1 a to the power r is congruent to 1 modulo m, where r be the least positive integer. Here a to the power st is congruent to 1 modulo m. Therefore, r divides st. Let this is number 13. Since GCD of R and S equal to 1, therefore from 13 we get R divides T. Let this is number 14. From 9 and 14, we get R multiplied by S divides T. This is number 15. Raising power S in 1, we get a to the power r to the power s is congruent to 1 to the power s modulo m. Implies that a to the power rs is congruent to 1 modulo m. Let this is number 16. Raising power r into, we get b to the power s to the power r is congruent to 1 to the power r modulo m. Implies that b to the power rs is congruent to 1 modulo m. Let this is number 17. Multiplying 16 and 17, we get a to the power rs multiply b to the power rs is congruent to 1 modulo m. Implies that ab to the power rs is congruent to 1 modulo m. This is number 18. Comparing four and 18, we get in 18 we see that ab to the power rs is congruent to 1 modulo m, and in 4 AB to the power t is congruent to 1 modulo m, where t be the least positive integer. Therefore, t divides Rs. This is 19. From 15 and 19, we get t equal to Rs, implies that since t be the order of AB modulo m equal to R multiply S, R be the order of A modulo m, S be the order of B modulo m, where GCD of R and S equal to 1. Proved. Now we verify the theorem for a particular example. Example. Let A equal to 3, B equal to 5 and M equal to 4. Here GCD of 3 and 4 equal to 1, implies that GCD of A and M equal to 1. Again, GCD of 5 and 4 equal to 1, implies that GCD of B and M equal to 1. Let this is number 1 and this is number 2. Now 3 square equal to 9. When 9 is divided by 4, gives remainder 1. Therefore, 3 square is congruent to 1 modulo 4. Implies that order of 3 modulo 4 equal to this power 2. Implies that order of A modulo m equal to 2. Let this is number 3. Again, when 5 is divided by 4, gives remainder 1. Therefore, 5 to the power 1 is congruent to 1 modulo 4. Implies that order of 5 modulo 4 equal to 1. Implies that order of B modulo m equal to 1. This is number 4. Let this is R and this is S. GCD of R and S equal to GCD of 2 and 1 equal to 1. This is number 5. Now A multiplied by B equal to A is 3 multiply B is 5, 15. When 15 is divided by 4, we get remainder 3. 15 square equal to 225. When 225 is divided by 4, we get remainder 1. Therefore, 15 square is congruent to 1 modulo 4. This is number 6. Since GCD of 15 and 4 equal to 1, this is number 7. From 6 and 7, we get order of 15 modulo 4 equal to 2, implies that order of 3 multiply 5 modulo 4 equal to 2, implies that order of 3 is A and 5 is B, 4 is M, that is order of AB modulo M equal to 2. This is number 8. Multiplying 3 and 4, we get order of A modulo M multiply order of B modulo M equal to 2 multiply 1, that is 2. This is number 9. From 8 and 9, we get order of AB modulo M equal to order of A modulo M multiply order of B modulo M. Here GCD of order of A modulo M and GCD of order of B modulo M equal to 1. Therefore, theorem is fit for this particular example. Now we prove a theorem. Theorem is so that if A is a primitive root modulo M, then A bar is also a primitive root modulo M, where A bar is an inverse of A modulo M. Let A be a primitive root modulo M. Therefore, order of A modulo M equal to phi M. Phi M be the Euler's phi function. This is number 1. Implies that A to the power phi M is congruent to 1 modulo M. This is number 2. Let A bar be the inverse of A modulo M. Therefore, A multiply A bar is congruent to 1 modulo M. Implies that A bar to the power phi M is congruent to 1 to the power phi M modulo m implies that a to the power phi m multiply a bar to the power phi m is congruent to 1 modulo m. This is number 3. Multiplying both sides of 2 by a bar to the power phi m, we get a to the power phi m multiply a bar to the power phi m is congruent to a bar to the power phi m modulo m. This is number 4. From 3 and 4 we get, here we see that left side of 3 and 4 be same, therefore we get a bar to the power phi m is congruent to 1 modulo m. Therefore order of a bar modulo m equal to phi m. Therefore a bar is a primitive root modulo m. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.